Okay. So it's my pleasure to invite Visu again. So he'll be giving a second talk on how to prove orbits are closed.
Okay, so this is a pretty difficult talk to give with any audience, I would say, and uh, kind of the main reason why it's difficult to give this talk to any audience is that most people are familiar with either very abstract stuff or most people are familiar with very concrete stuff. And in this talk, I'm going to try and take fairly abstract stuff and push it to really concrete computations because at the end of the day, what I'm trying to do is I'm trying to find some point and show that it has a closed orbit. So I have to do some computations. These computations cannot be entirely abstract if I have to do it for a specific point. At the same time, uh, the ideas come from fairly abstract. I have to basically break them down for you and show you uh, how things like these work. And the paper's up on archive. It's been accepted to a journal with minor revisions, but I encourage you to look at the archive version for like a lot more details. I'm going to keep skipping every now and then just because you have to believe some things on faith to see where things go. And this is of course joint work with Ham Duxon. Uh, so if you remember my previous talk, and I think most people were there, and if you weren't there, it doesn't matter so much. But just know this was my motivation for it, and the motivation for me was to prove degree lower bounds for invariant rings. Uh, and then there was this whole procedure that I had back there, and this procedure. So in the previous talk, I told how to do this in characteristic 0. And the kind of actions that I was interested in were things like SLN cross SLN cross SLN, acting on Cn tensor Cn tensor Cn with the 5 copies or something, or an SLN acting on Sim3Cn acting on 4 copies, yeah, some number of copies. Maybe it's not that important how many copies. Uh, but what I was very unhappy with was that when we first wrote that paper on exponential lower bounds. So for these we got sort of exponential degree lower bounds, which was the point of that paper. I was very unhappy with this guy. Very unhappy with characteristic 0. And so let me give a very quick overview of what we had to do there. So in there, I tried to use this thing called Groshan's principle. And it was, so you had some group that was acting on V and W, two different representations. And I took some point in the first one with a closed orbit, whose stabilizer was H. And then I said you have this kind of surjection between invariant rings. H. And so the degree bound here would be larger than the degree bound there. And so once I had this kind of setup, then I rigged it so that the right hand side, this W and H was like a torus action, and the way it acts on W was sufficiently complicated that the monomials that were invariant had to have an exponentially increasing sequence of exponents and so on. And I was able to rig it well enough. And the kind of points and the one main thing that I needed there was you need points with closed orbits. So if you have to ever do this explicitly, you have to be able to prove that some point somewhere has a closed orbit. And you want this point to have some sort of symmetries. Okay, so that's part and part of this motivation because you need this stabilizer to be somewhat non-trivial to actually have some non-trivial lower bound for that invariant ring on the right hand side. So in this motivation at least, and perhaps many other settings where you're motivated, need to prove, maybe let me not say prove, let me just say verify, or maybe let me say even try to verify whether points with symmetries have closed orbits. So I'm trying to emphasize on symmetries because symmetries are going to play a role in the technique that I'm going to try and explain to you. So one final thing about characteristic 0 is, well, why was this not a problem in characteristic 0? Okay, it is a problem. It's not completely solved or anything. But we do have this thing called the moment map, and uh, that can help you identify closed orbits. Okay, but that's a story that I don't want to be talking about today because it's not something I can do in general. So my main motivation was trying to do this in characteristic P, or really saying do this without analysis, any kind of analysis. And why? So that you can do for characteristic P. In my mind, it was utterly unimaginable that if I just replace this complex numbers in this invariant ring with a field of positive characteristic, that you would somehow not have this exponential degree lower bounds. But then when you can't imagine it and you think it's definitely true, you have to find a way to prove it. And the path is already shown to you in characteristic 0, and you see where the struggle is. And so you go and address the struggle as much as you can. And so let me give you an example of the kind of points that we are interested in. So remember, so I will take 3n, so three-dimensional vector space, and for it I will label a basis as xi, yi, zi, where I ranges from 1 to n. And the kind of points that I'm trying to really be interested in is something like sum of xi squared zi, sum of yi squared zi, and this is going to be inside sim3 of k3n 2 copies. It's fairly complicated. You can't do this that easily by hand by trying to find equations or anything of that sort. Even in the case when, let's say, n is 1, it can still be pretty hard to figure this out. Okay, so just x squared z and y squared z in sim3 of k3 two times. Okay, now the good news is that I can tell you whether the point for, whether the orbit of this is closed or not, and it will come through the techniques that I will try and explain over the next 50 odd minutes. But in order to explain the technique, I want to put myself in a slightly more of a baby setup, but I will still prove to you something you didn't know before. Okay, so I'm going to try and take as my example the polynomial, which is a symmetric polynomial in 3 variables. So this is the complete homogeneous symmetric polynomial in 3 variables. So I'm going to write it out once, just so that there's no confusion here. X cubed plus y cubed, plus z cubed plus x squared y plus xy squared plus x squared z plus xz squared plus y squared z plus yz squared plus xyz. And you somehow realize, you look at this polynomial and you think, okay, this has nothing to do with characteristic anywhere, and whatever behavior you have, whatever behavior you expect should really be a characteristic independent behavior. At least that would be the naive assumption. And you might think, okay, maybe characteristic 3 is a little funny because you're taking cubes, but it's hard to imagine which characteristics have unusual behavior, if any. Okay, so here's a bunch of questions that I have for you, and maybe you know how to guess this, maybe you know how to not guess this. Is the SL3 orbit of this polynomial closed? Does it depend on characteristic? Okay, for the rest of the stock characteristic of the lower field, I'm just going to call P. It's going to remain there. I don't want to keep writing P over, characteristic all over again. And I'm going to ask another question. And when you see some of the answers coming out in front of you, maybe you're able to guess how it depends on the characteristic. So there are some patterns that I can tell you that come out of computations, but I can't tell you what they really mean, or I can't guess it ahead of time. And I want to make one final note here is if you look at the moment map criterion, it doesn't work for this polynomial. You can test it. It's a very simple thing. I mean, in the sense like, okay, it might take you like 15 minutes to write down what the moment map is, but you write it down and it's not zero. And it's not obvious what your change of basis should really be to get the moment map to be zero, if at all it is zero, anywhere in the orbit. So even in characteristic zero, it's still a pretty hard question. So if you can, during the course of this talk, before I get to the answer, if you can tell me whether the orbit of this is closed or not in characteristic zero, and you have an idea why, I would be very interested to hear it. Hopefully, I mean, if it's something different from what I've come up with Harm, then so that's the kind of points that I'm interested in. But let me first tell you a little bit about what are the tools that we have. So to tell you what are the tools that we have, I will first explain to you an example with a different guy. So again, for the rest of this talk, or at least for the most part of this talk, the action that I'm going to be interested in is going to be SL3 on Sim3 K3. K3 is going to have basis x, y, z, and I'm looking at this is degree 3 polynomials in x, y, z. Okay, so for example, if I take if I look at the polynomial x cubed plus x squared y plus z cubed, I'm going to try and show you that this thing doesn't have a closed orbit. Okay, and okay, this is not a point with a great amount of symmetries. I just picked it so that whatever idea I had in mind was going to work. So here's how I do it. I look at this diagonal matrix lambda of t to be t, t inverse, and 1. So this diagonal matrix is an SL3 because it's a diagonal matrix and you multiply the terms on the diagonal, it's 1. To be concrete, what I mean is when I apply it on x, I get t times x. When I apply it on y, I get t inverse times y. When I apply it on z, I just get z. So what happens when I apply lambda t on f? So first one is x cubed. So that becomes tx whole cube plus tx squared t inverse y plus z cube. And if you, simplify it a little bit, you get t cube x cube plus tx squared y plus z cube. Okay, and the point is no matter which t you took, lambda of t is in the group, so lambda of t applied to f is in the orbit. But now if I take the limit as t goes to 0 of lambda t f, I'm going to get z cube. So I know z cube is not necessarily in the orbit, but I know it's in the orbit closure because I took points in the orbit and I just took a limit. So it's in the orbit closure. But then I'll also claim that z cube is not in the orbit. And this somehow I have to give you an ad hoc explanation because I don't have a great one. The only explanation that I have is if z cube was in the orbit of f, then f would have to be a cube of some linear power, of some linear function. But it's just not. Sorry, it's not. Okay, if you are able to apply some linear transformation to z, to go from z cube to f, then whatever z goes to, f would have to be the cube of that. But it's just not. You can find any number of ways to disprove it. Brute force is also fine because it's only 3 variables. Okay. So what I wanted to do was I wanted to basically explain to you this criterion called the Hilbert Mumford criterion. And here's what the criterion says. The criterion says that if your orbit is not closed, if and only if there exists what's called a one parameter subgroup, and I will explain to you what these things look like in any one case. So it's very easy to, such that the limit as t goes to 0, lambda of tv is not in the orbit. So what is the Hilbert-Mumford criterion telling you? It's trying to tell you if your orbit is not closed, then there's a very specific way, not unique. There's nothing unique about this one parameter subgroup. There could be many, there could be several different kinds of them, taking you to various points, but there's at least one sort of unified way in which you can take this point and go outside the orbit. And the way to do it is through a one parameter subgroup and a limit of that. Okay. Now, what is a one parameter subgroup? Well, I can say it's basically a map of algebraic groups. But I can tell you even more concretely what one parameter subgroups are for the group that's SLN. So if I take this, any one parameter subgroup is basically this. Okay, so I denote them as one PSG because I don't like writing the whole thing. Is of the form lambda of t is G, a diagonal matrix G inverse. So if you looked at the example that I told you, there I didn't do any conjugation, but here this one parameter subgroup was just a diagonal matrix where the diagonal entries were some powers of t. And if I look at it in more generality, it's basically those things up to some change of basis. That's what all one parameter subgroups are. And where really is the difficulty? The difficulty is not in the diagonal matrices. The difficulty is in anticipating what the change of basis is that's required. So if I told you you will find this one parameter subgroup with this particular choice of G, you can find it. It will be very easy to find that. But then trying to find this choice of G is the hard part. It's not always easy. Okay. So to be kind of pedantic or maybe boring, I will just point out, if I want to show that the orbit is not closed, this is a somewhat easier affair in the sense that I just have to show by magic, let me just say by magic, an appropriate lambda t. Okay. So if I just had to show that some orbit was not closed, by hook or crook, I can come up with this one parameter subgroup. I can dream of it, I can guess it, I can do whatever I want. And then that's a valid proof. If you can come with it, it's a valid proof. But if you want to show that it is closed, then you have to argue over all one parameter subgroups, which is a bit hard. You have to say no matter which one parameter subgroup you give me, it's not going to work. That's a much harder thing to give as an actual proof for any particular point. That's what we're going to try and do. And to do this, we come across a landmark paper of Kempf that's poorly understood. It's poorly understood in some communities. It's well understood in other communities. But the communities that understand it well don't speak to the communities that don't understand it well and actually have a lot of use for it. So here's Kempf. And I will point you to the paper. If you're not very familiar with representation theory and invariant theory, it's pretty unreadable. It was pretty unreadable for me, even though I had a background in representation theory for about 2 years. It's just called instability in invariant theory. I'm going to tell you exactly the kind of features that this proves, and it has these results in there somewhere, and they should be kind of very concrete by the time I'm done with it. So here's the gist of the paper, or at least the gist that I'm going to use. Suppose the orbit is not closed. Then Kempf tells you one thing, that there exists a unique optimal parabolic subgroup. I will explain all of these words in the case of SLN, because that's the best way to see it, called PGV. There's something unique about this and something optimal about it. And he tells you for any maximal torus, again, these sound like big things, but they're very, very concrete at the end of the day. For any maximal torus sitting inside this parabolic, there exists an optimal, again, he uses the word optimal, one parameter subgroup, lambda of t, inside this torus that drives V out of the orbit. And the third thing that really clinched it was he said the stabilizer will sit inside this parabolic. So let me give like a very quick understanding of what this optimality is for these one parameter subgroups, but it's going to be completely irrelevant for us. So what Kempf was trying to do was trying to say, among all the one parameter subgroups that are going to take you out of the orbit, you can put some measure on how fast it's taking you out of the orbit, some sort of gradient measure and so on. And he started proving some special properties of the one that takes you out of the orbit fastest. And the ones that take you out of the orbit fastest, he wanted to call optimal. And those things had a bunch of symmetries to it and some really nice properties, and he was able to prove things like this. Now I'm going to ignore this whole notion of optimality. It doesn't matter for me at all. All that matters for me is, instead of searching for one parameter subgroups, the entire collection of it, I will search for an optimal one parameter subgroup. And if I fail, then the orbit is closed. And if I don't fail, I will find for you an optimal one parameter subgroup, in particular some one parameter subgroup that will take you out of the orbit. So the idea, it's high level, but I still have to tell you how to implement it. Search for an optimal one parameter subgroup. If you fail, the orbit is closed. If you succeed, then you verifiably know that the orbit is not closed. And these properties that I've written, 1, 2, 3, will help me narrow down the search for an optimal one parameter subgroup. Okay, and that's going to be the clincher, is when you realize that these properties narrow it down so much that you can actually do computations by hand for many things that you didn't expect you could. So let me give the strategy, like a concrete strategy, before I start telling you what these parabolics and what these maximal tori and all of these things look like. So the concrete strategy is, first, collect all maximal parabolics. Not maximal, sorry. Collect all parabolics that contain this stabilizer. What did I write the stabilizer as? Sorry. Because these are the only parabolics that I have to look at. These are the only choices for this optimal parabolic subgroup. Once I do this, here is something where I have to put in a little bit of effort. I want to find a collection of maximal tori I'm going to put curly t, so that for any parabolic, so collect all parabolics, let me call this set script p, so that for any parabolic in this collection, there exists some torus in this collection such that this torus is contained in that parabolic. And it sounds a little complicated, but I want to just pull back to the earlier statement. So for any maximal torus, there exists a optimal one parameter subgroup. So among all these collections of possible optimal parabolics, you just need to be able to catch hold of one in each parabolic. So if the same torus exists in 7 different parabolics, you don't have to do 7 different checks for each of the 7 parabolics. Just checking for this one torus, this common torus is enough. So you just need to find some number of maximal tori so that no matter which parabolic that you can pick that contains the stabilizer, one of these things is going to be contained in that. And the third one is the final step. For each of these maximal tori, check if the orbit closure is contained in the orbit or not. But here's something that I tell you. When I stick down to a torus and I look for one parameter subgroups of the torus, orbits, orbit closures, limits of one parameter subgroups, these are very concrete. This is basically linear programming at the end of the day. It's very straightforward. There's nothing new or nothing hard to do once you get yourself down to a torus. Okay? So that's the key step. If you can get through 1 and 2 without getting yourself an infinite collection or like a, and sometimes you can work with infinite collections too, but if you can get through 1 and 2 with a manageable collection of toruses at the end of it, you will succeed in step 3 one way or the other. Okay. So that's the only catch. The only catch is hopefully this collection of maximal tori is manageable. So this is also where, for example, the fact that the stabilizer is non-trivial or the fact that the point has symmetries is something that comes up. Because if the point had no symmetries, then the stabilizer, which is the same thing as saying the stabilizer is going to be trivial, then in the first step, if I basically have to look at all the parabolics. And if I have to look at all the parabolics, then I've really not made my life any better. Because there's nothing that I can really cut down from the most naivest form of the Hilbert Mumford criterion. So it's also key there that the stabilizer is non-trivial. So it's not just enough for the stabilizer to be non-trivial. It has to be non-trivial in a way that it cuts down the number of possible parabolics. That's something that we see some of these things when it does. So now let me tell you about these parabolics and maximal tori and all. Okay, there's very concrete things. But I won't actually tell you what a parabolic is, but I'll tell you what it's indexed by. So parabolic subgroups of SLN are indexed by flags in k to the n. So given a parabolic, so given a flag, I will denote the corresponding parabolic by PF. So what are flags? Flags are basically subspaces that are contained in each other. So I think the way you go is you start with the 0 subspace, and then you put it inside something, and you keep putting it inside something, and at some point you end up with the whole thing. Okay, and the parabolic is basically the subgroup that stabilizes the flag or something. Okay, so these are linear subspaces, if that wasn't clear. So the Fi are linear subspaces. It's very concrete things. You can start writing some of these things down, and it's not so hard to get hold of them or understand how they look either once you start writing them down in basis. But maybe the key point that I want to point out here for us at least is that if the stabilizer is contained in the parabolic, is the same thing as saying that each of these subspaces that come in the flag are stable under this group action. Basically means I look at this stabilizer subgroup, and if I look at any of these Fi's in the flag, then when I act upon it with the subgroup, it stays within itself. It's a sub-representation for the subgroup. Okay. So if you think of what that means, what this means is if I look for parabolics containing the stabilizer, this is basically in bijection with the flags of stable subspaces. Okay. This is a key point, so I'm going to just hold for a second and let you just embed that. Without proof, I'm not proving anything here because these are all well understood. I mean, like, you can sit down and find yourself a textbook that explains this enough to you for you to be able to get this very, very straightforward once you know the right things to say. Okay. But what I want to really point out is that if you're looking for, so I'll pull back again. The first step was to collect all parabolics that contain the stabilizer. And if you want to understand all parabolics that contain the stabilizer, then you're basically down to understanding what are all the flags of subspaces that are stable under the stabilizer. Okay. Maybe let's also start calling this H. Just gets simpler for me. Okay. So you want to understand all parabolics containing a subgroup H is the same thing as understanding flags of H stable subspaces. Good. Now let's do this. Let's do this in the case of let's do it in the case of this polynomial. So let's take the example of H3xyz. This is this complete homogeneous symmetric polynomial that I had written down in the beginning, right? Sum of all monomials of degree 3. So in here, let's again remember the group is SL3. So, and what is the stabilizer? So what is the stabilizer of this complete homogeneous symmetric polynomial? Well, I don't know what it is. Maybe I don't really care what it is, but I do know that it at least contains the symmetric group. It is a symmetric polynomial, right? So if I swap around the variables, that's okay. It doesn't change it. So parabolics containing the H, or maybe let's just come down to at least the symmetric group. We have to basically then look for flags of symmetric group stable subspaces of K3. Now this is, if you've ever taken a course in representation theory, you know very quickly what this is, what are the stable subspaces here. And I'm again going to point out there's going to be a little bit of a difference between characteristic 0 and characteristic P, but actually you can just do this by hand and I will tell you what the answer is, and you can just do it as an exercise. S3 stable subspaces of K3 are basically 4 of them, 2 of them being pretty trivial: the 0 subspace, the span of x plus y plus z, the span of x minus y and y minus z, which, let me write it down in a different way, is c1x plus c2y plus c3z, such that sum of ci is 0. And the last one is basically all of K3. I will call the first one L because it's a line, and then I'll call the next one M because that's the other letter that I want to use. So what are all the possible flags? There's not so many. It's going to be 0 sitting inside L sitting inside K3, or 0 sitting inside M sitting inside K3, or just 0 sitting inside K3, or 0 sitting inside L sitting inside M sitting inside K3. But I want to point out this last one is only possible in characteristic 3, which I'll ignore for the moment. Okay, you just have to check that L is actually not a subspace of M unless you're in characteristic 3. Okay, so let's ignore characteristic 3 for now and focus on just these 3 flags. And I'm actually going to tell you, you can focus on just the top 2 flags. The last one always goes away for some obvious reason, for some technical obvious reason. You never have to consider that trivial flag. So it's just the first 2 flags that you have to consider if your characteristic is not 3. So let me go back again and go back to the strategy for a little bit. So the strategy was collect all the parabolics that contain your stabilizer. We just did that. And the next step is to find, maximal tori. You just want to find a set of maximal tori so that for every parabolic, there's one of maximal tori in my set that's sitting inside it. So let me tell you what maximal tori are next. Okay. So let's keep this in mind. We have two possible flags that we have to check for. So really, in this case, it's even simpler because you just have to find two maximal tori at most, one for each parabolic. Choose your favorite one and check. So let me tell you what maximal tori look like. So maximal tori of SLN. So there's the standard one, which sometimes people call STN, which is basically the set of all diagonal matrices. Okay. Product of DI equal to 1, so that you're inside SLN. So that's the standard maximal torus. And any other maximal torus is basically dependent upon bases. So maximal tori are in bijection with bases. So a basis might look like B1 to Bn. Okay, I did for SLN now, but yeah. And you can put this down in terms of a matrix B. And you can look at the subgroup, which is basically the standard maximal torus that's conjugated by B. Okay. And on the left-hand side, you have subgroups. So if you permute the bases, then you still get the same subgroup and so on. It doesn't, okay, but I don't care that it's not a one-to-one dictionary. I care that at least every maximal torus appears in this way. So up to a choice of bases, it's just diagonal matrices, right? So now the next step is, what does it mean? Actually, let me do myself a favor. Let me call this the maximal torus for the basis B. Just my favor. So what does it mean for a maximal torus to be sitting inside a parabolic? Okay. So remember, the strategy was find all these flags, the possible collection of flags that could be optimal parabolic subgroups. And then you want to find a collection of maximal tori so that there's, for every parabolic that you want to that you care about, one of these maximal tori is sitting inside it. What does it mean that it's sitting inside it? Well, any parabolic is associated to a flag, right? F1, dot, FD, which is the whole space. So this is the same thing. Maybe I should say equal to. This inclusion is the same thing as saying each Fi is a coordinate subspace in the basis B. What does that mean? That just means that if I look for each of these vectors, each of these subspaces in the flag, they should be spanned by some subset of B1 to Bn. Okay, so maybe I'll just write that down because this term is not entirely clear, but Fi is equal to span of some subset of B1 to Bn. That's what it means. Great. Now you have your parabolic subgroups. If you want to find a maximal torus, you have to come up with a basis. What does this basis have to do? This basis just has to make sure that each of the subspaces in your flag is a coordinate subspace. So what is the one way you can do? You can just go in your flag, start from bottom to upwards, and pick a basis so that at every point it's a coordinate subspace. So you pick a basis for F1, then extend it to a basis for F2, then extend it to a basis for F3, and so on. Okay, so that's maybe I can just quickly write it down. So take a basis for F1, extend to F2, and so on. So if you do that, then you get a basis, and that basis that you get, the corresponding torus, the corresponding maximal torus for that will be contained in your parabolic. Okay. Again, very concrete. Okay, so let's go back to our favorite polynomial, to my for this talk at least. Let's go back to this example. So I will have to recall this because I know this, but you've probably forgotten it now. There's two possible flags, right? Where L was the span of x, y, z, and M was the span of x minus y and y minus z. Good. So let me pick one of them, and to let me to be more illustrative in nature. The first one, no, nothing. Okay, so there's one and there's two. Okay, so I'm going to just say it out, but you can look at the computation. Fact one, nothing non-trivial comes out of one. But you can do this check exactly the way I do too. So I will just show so I'll just show 2. Okay, so I have this parabolic. Cannot do this. Go back to this. So I have this parabolic, and to this I want to come up with a basis. And what is the basis that I will pick? Well, as I said before, start with a basis for M and then extend to a basis for K3. Very easy. So I start with a basis for M, which is already given there, x minus y, y minus z. And then I want to extend to a basis of everything. So I will just put a z. Okay, so that's a basis. And now I claim that if this is your parabolic, the torus corresponding to B is sitting inside the parabolic. Okay, so this you can check. Okay, so let me go back again to the strategy and see what's the last piece that you have to do. So we've identified a bunch of toruses, one for each flag maybe. So in this case, we've identified one torus. And then for this torus, I want to check what's happening with the orbit closure. So for example, is the orbit closed or not? Does there something exist in the orbit closure with respect to this torus, right? Not so hard. And if you've ever worked with torus, you realize that all you have to do is plot what's called the Newton polytope, or what's called the weight polytope. So I have to figure out what the non-zero weights are. It's going to be some convex polytope. I'll look at it and I'll see whether the origin is inside it or not, or whether it's on the boundary or not. And in this case, it's going to be a two-dimensional picture, so I'll draw it for you, and you'll see it. And then you'll see some numbers that just have funny behavior with characteristic. So let me just put this down. Need to understand the orbit and the orbit closure. Okay, so let's do it. Now here's the funny thing. We don't like working in all kinds of bases. So we always want to pull back to the standard basis, right? So I wanted to understand so this torus here is like the standard torus conjugated. And I want to understand what it is here. So instead of doing all of this, which is going to be a bit of an annoying mess, what I'm going to do is I'm just going to write H3 of x, y, z in the basis B, and then work with standard torus. This is a completely valid thing. It's just like a change of basis that you have to learn once in your life. And then the only thing you'll ever get confused of is whether you should have used B or B inverse, but different story. Okay, so let's not worry about that. Now let me tell you what you have to do. So I have to write this in the basis B. So this basis B was x minus y, y minus z, z, which let me call for the time being ABC. So if I have to write H3 of xyz in the basis ABC, then I have to first write x, y, and z in terms of ABC. So if you realize x is going to be a plus b plus c, y is going to be b plus c, and z is going to be just c. So H3 of XYZ, if I want to write in terms of ABC, is like A plus B plus C, B plus C, C. I won't tell you what this complicated computation is. I won't tell you how to do it because all you have to do is plug it in and write it out. And you will get it, and you will get it to be this. So H3 of A plus B plus C, B plus C, C is going to be, I don't know how else to do it other than write it down for you once. A cube plus 4A squared B plus 6AB squared plus 4B cube plus 5A squared C plus 10AC squared plus 10C cube plus 15 B squared C plus 20 BC squared plus 15 ABC. It's a computation. I don't have to justify it. Just do it. So now what you have to do to understand this torus is you have to write down the weights here, which if I explained this a bit last time, but really just write down, just plot the Newton polytope. Okay. So plot the Newton polytope, which basically says plot all the exponent vectors with non-zero coefficients, which in this case is going to look like a triangle. And in this triangle, this guy here is going to correspond to A cube, B cube, A squared B, AB squared, this is C cube, and so on. So I'm going to replace the dots with these numbers. So I have 1 here, 4 here, 6 here, 4 here, 5, 15, 15, 20, 10, 10. Okay. And now you have this Newton polytope, and you have the center of the Newton polytope, which I'm going to give a nice little funny color. So you have the center of this Newton polytope. So in this case, if you were in characteristic 0, then this Newton polytope contains the center. So characteristic 0, Newton polytope contains center. I should really say that pink dot, which means the orbit is closed. Okay, that means dB.V, dB.H3 XYZ is closed. So you might be thinking, what is about this center that I'm really looking at? So these exponent vectors, this looks like 3, 0, 0, 0, 3, 0, 0, 0, 3, and 2, 1, 0, and 1, 2, 0, and stuff like this. You should think of all of these modulo this, modulo the line of the line spanned by 1, 1, 1. Okay, so that's why it's a truly two-dimensional picture, even though there's 3 coordinates floating around to it. And if you look modulo this, then when I draw this two-dimensional picture, that center point will become the origin. And so for torus actions, you write this thing, it's the Newton polytope here is called the weight polytope in general. And if the origin is in the interior, then the orbit is closed. If the origin is outside the interior, then it's not closed. So then there's 2 ways it can happen. The origin could be on the boundary, or the origin could be outside. Okay, so for all purposes, origin for now is this pink dot. Okay, so in characteristic 0, this is fine. But now you see these numbers that show up: 1, 4, 6, 4, 5, 15, 20. What are the only prime numbers that are really showing up here? There's 2, 3, and 5. Okay, we've forgotten about characteristic 3 because this is not relevant for that. That you have to do a separate computation. Similar one, but it's a separate computation. So really, the 2 possible offending primes are 2 and 5. If your primes are not 2 and 5, the same picture holds. So this already tells you that if the characteristic is not equal to 2 or 5, that implies this orbit is closed. This corresponding with the other parabolic computation that I said nothing funny comes out of it, which you have to believe me, but you can just do it. This plus computation for other possible parabolic. All of this implies that SL3 orbit is closed. Okay, so I'm going to write this down on the next page. So if the characteristic is not 2, 5. Newton polytope contains origin. Therefore, along with the analogous computation for other parabolic, you take all of this and you conclude that SL3 orbit of H3 is closed. Isn't that great? Like, we start with the problem with SL3 and H3 and we're looking for orbits of being closed. And by the end of the day, we came down, we drew like 10 points and we said, okay, some of these are non-zero, some of these are zero. And you could do this for P not equal to 2 and 5. And I picked this case because I want to show you what happens in the case of P is 2 and P is 5. Because it's really funny. And you can actually see, this is when you realize that your technique actually works. Because in these cases, it won't be closed. And I'll show you why it's not closed by showing you something in the closure. It just pops out. So when P is 2, so look at this same picture. When P is 2, 1, so this 4, 6, and 4 die. Everything else, sorry, 4, 6, 4 dies. 10, 20, 10 also dies. Only 4 things remain. So when P is 2, the only things that remain are this. Okay, so I will draw this. And I think by now you realize that it's just the support that matters. So when P is 2, it's just this guy here, this guy here, this guy here, this guy here. So that's the polytope. And the center is on the edge. Okay, so that's great. So in this case, origin on the boundary of the Newton polytope. So, and if you work with torus actions enough, then you know how exactly to go to the closure. You can kill everything on the 1/2 space that's kind of protruding out. So I can kill this extra dot here. So I can sort of kill this guy. And I will tell you exactly how to do it. It's very straightforward. So I'll take the 1 parameter subgroup, which is t to the minus 2, and t. So in other words, lambda t acting on A is TA, acting on B is t to the minus 2b, and lambda 2 acting on C is TC. And let me tell you exactly what it is, right? So in characteristic 2, if I write H3 of x, y, z as H3 of A plus B plus C, B plus C, C, all of those things cancelled out, right? All of those extra terms with the coefficients that are even, they all cancel out. And the only thing you're left with is this thing simplifies somewhat to A cube plus A squared C plus ABC plus B squared C. And if you apply this lambda t, it's kind of clear what happens. So I get a t cube A cube plus A squared C. Sorry, I got this bit wrong, maybe. Squared C, no. I got this just a bit wrong, but thankfully I can solve this easily. Okay, so A squared C, so t cube A cube stays the same. A squared C now becomes just A squared C. ABC also becomes ABC, and B squared C also becomes B squared C. And then if I take limit as t goes to 0, that kills this guy. And if you see what this is going to be C times A squared plus AB plus B squared. And then you somehow guess or check that, okay, so what is the conclusion here? The conclusion here is that C times A squared plus AB plus B squared is the limit as t goes to 0 lambda t of H3 of XYZ, whatever it is. So this thing is in the orbit closure. Okay. But then I claim if you use Eisenstein's criterion, you will get that H3 is irreducible. Which means this guy cannot be in the orbit. Sorry, because it is reducible. Okay, that's great. Now what happens in the case when P is 5? It's even stranger. It's something that you don't expect at all. So if you remember these things, I will write the numbers down again because I have them in front of me. 1, 4, 6, 4, 5, 15, 15, 10, 20, 10. And this was the center point that you care about. And this number is 15. Now, if I'm looking at characteristic 5, then all of these things get killed. All of these guys get killed. And the Newton polytope is just this. And if you see that that's what the Newton polytope is, now you realize that the origin is actually outside the Newton polytope. So origin outside Newton polytope, which actually basically just means that H3 is in the null cone. It's very hard to guess this. That in characteristic 5, the complete homogeneous symmetric polynomial is in the null cone, which all this really means is that origin is in the orbit closure. Which, by the way, from this you can actually figure out what that one parameter subgroup is, apply it and check that you have a sequence of elements that actually takes you all the way down to 0 in the orbit. Which is just great. So with all these computations, let me just tell you what the conclusion here was. The conclusion here is I looked at H3 of XYZ and the SL3 orbit is closed if P is not equal to 2 and 5. It's not closed, but not in the null cone if P is equal to 2, and in the null cone 1, 2, 3 in the null cone if P is equal to 5. And you can do many things. You can ask for many things. So for example, like one of the things that we prove is like Schur polynomials. They have closed orbits. Well, if the number of variables is sufficiently large and things like that, even in characteristic 0. And then, for example, you can use this. You have to refine this a little bit more, maybe a little bit more difficult analysis, but you have an algorithm to decide if a symmetric polynomial has a closed orbit or not. If a symmetric polynomial has a closed orbit, this is actually pretty efficient in characteristic 0. It's only about as efficient as you can get because symmetric polynomials take a long time to write once you ask for enough symmetries. And in positive characteristic, it's not quite as efficient because at one point I have to do Groshan bases. And so one final point that I want to make is there's one issue that we keep running into, and I keep running away from it by giving you some trick or the other. So I'll point it out right here. So you can do these things and you end up with this possibility of an optimal one parameter subgroup, and you take this limit and you can come up with this limit, and then you want to know whether it's in the orbit closure or not. And I keep coming up with some funny trick like, oh, this one's irreducible, that one's not. This one's a cube, that one's not, and stuff like this. But you don't have to always do it. The one thing you can do is, it's in the orbit closure, but it may or may not be in the orbit. So you just have to understand the dimension of the orbit of this new thing,
Hmm.
which is the same thing as understanding the dimension of its stabilizer. If its stabilizer has a larger dimension than the stabilizer of the initial point, then it cannot be in the orbit, it has to be in the closure. And computing the dimension of its stabilizer, you don't have to compute the stabilizer, just its dimension. In characteristic 0, for example, is a Lie algebra computation. So it'll boil down to some kernel of some matrix. Not so hard. In positive characteristic, that's much harder. Uh, but yeah, I mean, there's challenges here, and some of these results, especially for symmetric polynomials, if you want to see when when the orbit is closed, or semi-stable, or polystable, and things like this in positive characteristic, it boils down to some pretty interesting and delicate combinatorics involving these kind of numbers that show up and whether they vanish because it's yeah, basically these kind of numbers, right? There was no way for me to guess ahead of time, even knowing now that the numbers that were going to show up are 1, 4, 15, 10, 20. I mean, I don't know where to get this kind of intuition from. So if there are some combinatorics, I mean, if there are people in the audience who are really interested in algebraic combinatorics, you can try and look at some of the things. I mean, I've tried to do it as far as I could in the paper, but of course, I mean, you can clearly see that I'm stuck in many places because I don't know how to handle the combinatorics. And if you can have some insights, I would be very happy. Okay, so I will stop there.
Lovely. Yeah. So, I mean, I just went to the paper on the archive. So you also say there are some representation theoretic methods you have. What are the when you say representation theoretic, are they actually certain representations or?
No. I think this is really what I meant by like going through
This is
parametrics and maximal
okay.
corollary.
Okay.
That's what I really meant, yeah.
Okay.
As
Very
opposed
nice.
to like taking the moment map or something.
Yeah.
I have a very naive question. So your talk today was based on the Hilbert Mumford criterion.
That's right.
So where you are trying to derive your point to something that's in the orbit closure but not in the orbit.
Yes.
And your previous talk was based on the moment map, where I think you are trying to drive a point to 0. So could we say then that this Hilbert Mumford criterion is in more general because you don't focus only on 0 but on any point in the orbit closure?
The Hilbert Mumford criterion is more general, but the moment map, you're actually not trying to drive it to 0. To be precise, in the moment map, you're actually trying to, I mean, there's not driving, but in that kind of optimization that people talk about, looking for like, you're trying to drive to like the point of minimal norm. So you're trying to drive the gradient to 0.
Yes. Okay. So you're trying to get to 0 as closely as possible. So it's a criterion for you can show that a point cannot be driven to 0.
Correct.
Yes. Okay. But you focus on this particular point 0.
Yes and no. I think yeah. I mean, the moment map has its own disadvantages and advantages. The moment map has its disadvantages that you can't use it in positive characteristic. But at the same time, the way we were trying to capture, so here's the main difference. In this approach, at least, if it works out at the end and you're able to do the computations by hand or with a computer, it doesn't matter how. At the end of it, there's going to be a conclusion. Either the point is closed or not. With the moment map criterion, you won't be able to tell if the point is not closed. If the moment map vanishes at some point in the orbit, yes, it's closed. But if you can't find that point, there's no good way of finding it, because if you try these approximation algorithms, you will keep coming close, but you'll never actually hit it, right? You'll run into numerical issues, you'll run into everything, but you won't actually know whether you're hitting it or coming very close to it.